American Meteorological Society certified consulting meteorologist. During his career, he has performed research as an Air Force weather officer, small business owner, private consultant, NASA contractor, and research professor at North Carolina State University and the University of Nevada, Reno. His main research focus presently is on multi-scale dynamics, forecasting, and modeling of extreme western weather. So today he will be talking to us about the scale of atmospheric processes that create localized extreme heat bursts, dry lightning, wildland fires, and debris flows in the West. Welcome.
Thank you for having me. This talk is basically focused on the whole issue of how the atmosphere organizes the ecological cascades that are extraordinarily devastating to the environment. What we're really looking at is how the large-scale atmosphere interacts with local terrain to produce a scenario in which dry lightning occurs after extreme heat. The dry lightning, of course, is associated with thunderstorms that produce lightning, but very little rain. That triggers fires. The fires eventually are amplified by downbursts from the cool downbursts or microbursts from the thunderstorms. They spread, become disasters. Then eventually thunderstorms spread upscale and become major rain producers, leading to landslides and devastating effects on the fire-affected terrain. So this is really an important component of what climate change can affect, both natural, of course, and man-made climate change. Now, in terms of the specific topics we'll be talking about today, we'll be talking about what causes the larger scale atmospheric planetary waves to break that set up the environment, the large scale environment for this type of phenomena. What is the link between wave breaking and extreme heating? How does a record heat event in Los Angeles translate into one in Utah? Yes, that's true. We can show you how that's going to happen, or how it has happened. And why do fires and flash floods follow the heating? So we're really trying to link the atmosphere driven by climate to ecological disasters in a very complex cascade process. All right, first of all, let's talk about planetary wave breaking. I know a lot of you are not meteorologists, so this is a strange term. But planetary wave breaking is really a critical link between long-term climate forcing and short-term atmospheric extreme events. We're talking about linking multi-month, multi-year forcing to periods of just days. And this is a very, very interesting phenomenon. Planetary wave breaking occurs over scales of motions typically on the order of 5,000 to 7,000 kilometers. That's continental scale. What you see before you is a sequence of upper level charts. The red areas represent high pressure aloft, the blue areas low pressure aloft. And over a period of just a few days, what happens is that the jet stream buckles and produces a massive ridge of high pressure over the western United States. That massive ridge of high pressure is occurring right over that little yellow dot. And the little yellow dot is an area where dry lightning produced extreme fires. More than 10,000 acres were burned over northern Nevada. This occurs over just a few day period. And that rapid amplification of the upper level ridge is important for producing extreme heating that leads to this type of cascading ecological disaster involving fires. To give you a sense of the physics of this, basically when the upper level ridge forms associated with planetary wave breaking, there's a lot of mass aloft. That mass has to go somewhere, so it sinks. When it sinks, it compresses and it warms. As it warms, of course, it produces a very hot pool underneath it. It also scours out all the cloudiness because the relative humidity decreases. That allows solar insolation to heat the ground, and ground, of course, produces surface-sensible heat flux. So the combination of this sinking motion due to Rossby wave breaking and surface heating due to the scouring out of the clouds produces a very deep, well-mixed hot layer. And that produces a scenario where you get flash drying at the surface and the fuels begin to dry very rapidly. Next, what happens is that when you get one of these very deep, hot, well-mixed layers, several kilometers deep, any atmospheric disturbance, such as a flow of air off the Pacific Ocean or from the Gulf of California or the Gulf of Mexico, can produce an elevated plume of moisture. When that elevated plume of moisture moves over this very deep, well-mixed hot layer, thunderstorms can develop, but the thunderstorms are very high-based. Sometimes their bases are as high as 5 kilometers above the surface. They don't have a lot of moisture because this occurs typically over the Intermountain West. And the thunderstorms produce lightning, but very little rain reaches the surface. This is your mechanism for producing the fires. Once the fires occur, cool downdrafts from the thunderstorms that are occurring under very dry air produce very strong gusty winds which spread the fires. Eventually, as the thunderstorms grow upscale, they produce heavy rain. The fires destroy the hillsides, which in turn leads to debris flows and landslides. So that is how this whole process really gets going. Dry lightning is typical in the West. As a matter of fact, a very significant portion of fires that occur in the West are associated with dry lightning. An example that you see in front of you, two of the recent examples from just June 2016, are the so-called Pyramid Lake Tribe Reservation Fire and the Tilley Fire. These occurred in northern Nevada, and on the right-hand side you see the devastation, lower right-hand side. Actually, yes, your lower right-hand side. And you see the smoke plume from the fire in the upper right-hand side. And you can see in the figure on the lower left, the broad area that's burned. You're talking hundreds and at times thousands of acres. So this process that I'm going to discuss today is critically important for the ecology of the West and occurs every year. Now, an example of this very rapid extreme heating where the large-scale atmosphere sets up a scenario where you get this type of ecological problem is the recent 2010 Los Angeles heat burst event. Now, I know you're thinking, what does Los Angeles have to do with fires? Los Angeles itself doesn't, but Southern California does. This is a widespread fire event that occurred during a period in late September in Southern California. And what's so amazing about this extraordinary heat event, it produced the warmest temperature in Los Angeles, 113 degrees Fahrenheit, the warmest temperature in many locations in Southern California. And not only did it occur on 27 September, which shows you the importance of the large-scale flow and organizing it, this occurred in fall and autumn, but the 113 degrees at the Civic Center in LA occurred at 12:30 in the afternoon. So you can imagine the dynamics that were driving this extreme heat event. And this type of thing on a smaller scale often occurs in the West to produce this ecological cascade. The chart you see in front of you represents several surface stations that were recording temperature. And you'll notice that on the 27th, shortly after 1200 UTC, or just before 1800 UTC, 1800 Greenwich Mean Time, several stations approach 112 to 114 degrees. So this occurred over a fairly large area of Southern California. The chart you see in front of you sort of synthesizes the scale of this, showing Southern California from basically the central coast down to San Diego, inland into western Arizona. The little dots represent the locations where all-time record temperatures were set. The brownish areas represent the hottest, getting up to 114 degrees. The size of the circle gives you a sense of the longevity of the previous record before it was broken. So you can see the scope of this type of heating event we're going to talk about today. Now, we've done a lot of research. My colleagues and I have done a lot of research on this case study, and we've used computer models and we've used observations to do this research. The diagram in front of you is a little bit technical, a little bit wonky, but really important, because in our research, what we found is that 3 distinct heat plumes triggered by this large-scale Rossby wave break were responsible for the extreme heating event over Southern California. The lines on that diagram, the color lines on the diagram, represent the location of atmospheric trajectories that were simulated. Those trajectories simply tell you where air parcels came from in four-dimensional space and time. And based upon our trajectory analysis, which tells you where parcels are moving from, we determined that there were three specific heat plumes that occurred on this day. One heat plume that moved off the Pacific at mid-levels and moved down the California coast. That's heat plume 1. Heat plume 2 drove all the way across the Great Basin from southern Wyoming, southern Utah into Los Angeles. And heat plume 3 was associated with an event that moved from western Arizona all the way into LA. And this occurred over a multi-day period. So each heat plume basically reinforced the subsequent heat plume, and it drove hot air down to lower levels. The cross-section on the lower part of that particular diagram shows you the vertical distribution of where these plumes came from. And you can see that when you look at heat plume 1, heat plume 2, and heat plume 3, time is changing across the bottom, so you have one plume descending, another plume descending, another plume descending, all under this massive ridge of high pressure associated with the Rossby wave breaking. So you can see that action at a distance can create local conditions just ideal for ecological disaster. Of course, action at a distance is what climate change will set up. Briefly want to show you a schematic of where these three heat plumes developed. Heat plume number 1 is associated with circulation off the eastern Pacific as that massive ridge started to amplify, and basically came in from the southwest towards Los Angeles and Southern California. Heat plume number 2, associated with the blue arrow, developed over the Intermountain West, and the trajectory for that, the descending trajectory for that under the massive ridging, basically can be traced back from off the Pacific to across eastern Wyoming, southern Utah, and into Los Angeles. And finally, heat plume number 3 is really remarkable because heat plume number 3 basically developed as the massive ridging across the west triggered another ridge along the Pacific coast in the subtropical jet. These two combined to produce a heat plume from basically New Mexico that descended into Los Angeles. And what's really fascinating about this third plume is that it's very similar to propagating easterly waves that developed south of the Sahara, south of the massive ridge of high pressure over the Saharan desert. And this particular propagating easterly wave made it all the way down, produced heating that made it all the way down to the surface, and produced the final heating in this sequence of events. Point being is that massive circulations can produce local heating that can lead to ecological disasters. And climate change, whether natural or man-made, can set up the scenario that leads to these types of extreme events. And these are the types of extreme events that may become more prevalent in the future. Now, of particular interest to those of you that live in northern Utah, or those of you that live in the northern part of the Great Basin in general, one of the really fascinating things about this event is that while on 27 September you had the record heating, the extreme record heating in Southern California, if you look at the diagrams, you see this is the temperature on the 28th of September and the temperature on the 3rd of October at 2,000 meters above the surface relative to mean sea level over the Great Basin. The red area represents extremely hot air. You'll notice that the red area across southern Nevada and California and northern Arizona associated with the record heat actually pivots northward and ends up over northern Utah just 4 or 5 days later. So what starts out as a heat event in Los Angeles actually propagates throughout much of the Great Basin. This particular figure you see is a surface representation of variables at Logan, Utah, 5 days after the LA heat event. The various plots represent temperature, dew point temperature, and pressure and sky conditions. If you look at the top, let me see if I can get the pointer to work here. Yes, it does. if you look at that top curve over there is the temperature at Logan, Utah on October the 2nd, 5 days after the LA heat burst event. That's 91 degrees Fahrenheit, the warmest temperature ever recorded in early October in Logan, Utah. So the air from Los Angeles, that was the end result of the Rossby wave breaking that produced the extreme fires in Southern California, was actually transported back into Utah. So the heat burst essentially spread throughout the Great Basin. Now, following that event in Logan, Utah, the record heating in Logan, Utah, the whole sequence of ecological cascading unfolded. What you see before you are two examples of meteorological soundings. And all this is a chart showing what happens when the weather balloons released at Salt Lake City. And these represent basically pressure decreasing with height, temperature increasing across the lower axis. And when you look at these two different soundings, one's on the 3rd of October, the other's on the 4th of October. The two solid lines represent what the balloon senses when it's released from the surface up to about 16 kilometers in the atmosphere. The solid line on the right of each diagram represents ambient temperature. The one on the left, dew point temperature, which of course is the temperature to which the air must be cooled for saturation to occur. Also shown on this diagram are winds on the right-hand side of both diagrams. The barbs show the direction from which the air is flowing. If you look at the diagram on your left, the beige diagram, that's late afternoon on the 3rd of October. The next day is the same diagram on the 4th. Notice two things change when you compare these diagrams. Up at about 15,000 feet above the Earth's surface, those two lines converge. What's happening is that a moist plume is being transported into that deep, hot volume. That moist plume is going to set off dry thunderstorm activity. And notice the wind barbs on the right-hand side of each diagram. Notice how they change radically in direction. That's the jet that's transporting the moisture into that hot environment. This is a MODIS satellite imagery showing the atmosphere on the 3rd and 4th of October. The one on the left represents the southern part of the Great Basin on the 3rd, and one on the right on the 4th. You can see how clouds and thunderstorms populate the one on the right. Just 24 hours later, consistent with that sounding, it showed the moisture being transported. So basically, the heat event is being followed by dry thunderstorm activity. And that dry thunderstorm activity will become upscale, moist thunderstorms very quickly. Here's the proof of the lightning strike from the lightning strike network. The little red areas represent lightning strikes. So by the time the 5th of October comes around, lightning becomes ubiquitous over the Great Basin. This triggers fires. The fires start the ecological cascade. Here's two more meteograms. The one on the left is Provo. The one on the right is Logan. And the important takeaway here, and it's a little bit complicated because there's a lot of stuff on the diagrams, but the important takeaway here is the following. If you look at this number over here, this represents the surface wind gust. This is at Provo on the 4th. This number up here represents the amount of precipitation that fell during that time period. No precip fell, but there's an observation of precip and a surface gust to nearly 30 knots. That's a dangerous scenario that can spread a fire due to dry lightning. The next day, or the same day, over at Logan, what you see is a thunderstorm over here with a surface gust of 35, and what you can't see over to the right is the fact that no precipitation hit the ground either. Dry thunderstorms are occurring, strong gusty winds, starting the ecological cascade. Whoops. Finally, the last wonky technical slide I'll show you. Finally, here's the Mediagram for Logan. And this is on the 8th of October, 3 days later. The important takeaway here is that you have significant precipitation, as indicated by 0.04 in 6 hours, 0.18 inches and 0.12 there. And that means that that area that had dry thunderstorms now has moist thunderstorms, setting up a scenario for potential landslides and debris flows. And for those of you who may not know how powerful and how devastating a landslide and debris flow can be, this diagram should make that painfully apparent. The figure on the top side of the diagram represents all the little Technicolor areas, represent Southern California where a significant amount of burning occurred during a recent fire event. You can see that some of those areas are almost county in scale. The lower diagrams are obviously a scenario where a neighborhood was inundated by a landslide triggered by the heavy rain following a fire in Southern California. So the ecological cascade shows an entire neighborhood being covered in debris as a result of heavy rains that followed a fire that was caused by dry lightning that was before that caused by massive Rossby wave breaking associated with heating. So these types of ecological disasters may be something we see more of in the future, depending upon how the evolving climate scenario changes or modifies the atmospheric circulation, which is a very, very complicated problem to solve, and we haven't solved that problem yet. So in summary, what are the fundamental questions that all hydrologists, atmospheric scientists, and ecologists need to worry about? Will climate change after planetary wave breaking or Rossby wave breaking patterns in the West, how will that modify these patterns? This is a critical, important question. How can we improve the forecast of dry lightning outbreaks in order to organize available fire suppression resources? This requires very close collaboration among Western U.S. Hydro, atmospheric, and ecological research communities. This really brings together those three communities in terms of what evolving climate will do to this problem. So to summarize, a double planetary wave break results in multiple heat plumes, record Southern California heating. Residual winds and circulations following the third heat plume affect Southern California, and this moves into the northern Great Basin. Southern California heat plume propagates to Logan, Utah, sets daily heat record. Mid-tropospheric moist jet follows the plume, organizing high-base thunderstorms, gusty shifting surface winds, sets up conditions for post-fire debris flows, and raises the serious issues of how our three communities are going to anticipate natural hazards, natural ecological cascades as a function of our evolving climate. And I simply want to acknowledge our sponsor for this particular research, the National Science Foundation Physical and Dynamical Met Division. Thank you.